So, hello everyone. So, as promised today, we're going to discuss in more detail what critical sections are and lock are. So to reply the question that I was asked during the practicals, why on earth we are going to use locks if we already have like atomic operators? So what is actually the purpose of doing this kind of stuff? So in here, we're going to see that in here, we might need, as we've seen in the first set of slides, to protect an entire region of the code, because while you're updating one variable, then the update of one variable might be dependent on the update of the second, and therefore, as a consequence, you want to make all the operations atomic, and I also was asked what atomic means. It means in one shot. So either I do the operation or I do not that completely. And so that is what we're trying to do now, to use mechanisms in order to enforce that. So we're going to start from the lower level up until to have something at the higher level. But besides that, before I start blabbering about this kind of stuff, do you have any questions? Okay. So in summary, in here you're going to see what we're going to talk about today, which is the things that you see in green, the diagram above. So we're going to see software-based solutions, which are busy waiting. Why? Because in busy waiting, I just wait for a condition to happen. And so I'm not using nothing at all on the architecture for doing that. I'm just waiting for a condition, more or less. And test and set, which, is actually quite a spurious definition of software-based, because in here we're not going to use in Java like any kind of processor-provided operations. But nowadays, even in modern architecture, you also have test and sets at the instruction level of the processor itself. So it's quite a spurious definition. And then you have scheduler-based approaches which are using, this is actually more clear and precise, the scheduler within the Java virtual machine, or what have you, to orchestrate or to direct the order of executions of the agents. For which then you have, we're going to see today, locks. And in this afternoon, the monitors. And then I agree that at the end of the slides, you have Decker and Dijkstra algorithms, but we're going to see that and postpone to the last lecture, because that is more an advanced application of something. And as far as I'm concerned, you only need to understand what is the idea of the Decker and Dijkstra algorithms, or Peterson algorithms. What are they trying to fulfill is basically having a lock, as we're going to see today, in a software-based way. But besides that, then the task of today is actually trying to answer some of your questions that beforehand you were only seeing from the application of a strict two-phase locking, so you have some region of code and doing operations. But from there, even for you, it was not clear what was the purpose, because the variables were not mutually independent. So it was just updating one variable and then updating the other. So what is actually the purpose of locking an entire region of code? Then the actual answer will also come from your coursework. So even in there, you would see, whenever you're doing the tests, that even though you're isolating one variable by itself, then you're not guaranteeing that something bad will happen globally. So you will see also from the application of the coursework that you need to ensure that the entirety of the region is actually protected in reading and writing, not just one variable at a time. So you need to define that first which regions are critical, thus define critical sections, identify the properties describing concurrent programs. Why is this relevant? Because as I was always saying, if you don't know how to, so if you know the language that we're describing, then you know also to name the problem and to look for the problem and to solve the problem. Otherwise, you know that you have a problem, so you need to baptize somehow the name or give a name to the thing that you're having. then you need to identify which properties should a program guarantee in critical sections, because it's not even irrelevant that I have properties, but problems of programs, and to define critical sections. But then I need to know which are the things that needs to be guaranteed. And then we're going to introduce some kind of software scheduler, shared memory synchronization strategies by using any kind of so-called design patterns on top. But we're going to start gradually and as much as possible from the simpler part. So we're starting with, as usual, with some problems, so we're already facing the truth. With non-interference, basically the thing that you're having is, if you're not using specific atomic constructs, so not necessarily atomic integer, atomic class, but something that makes the code atomic when required, it might happen that a thread might need to access variables shared among other threads, and then therefore you're generating race conditions. Yet again, you have a race condition, I'm just reinforcing the idea. You're having a race condition whenever you have a variable or a set of variables that are accessed both in reading and writing, for which you have a problem of spurious information or not clean information being inside. And so you want to prevent that the data might be partially updated, not completely updated, or you're seeing data which was not meant to be seen. So then the question is, how do we then guarantee the atomicity of operations? So as someone was asking, then you could also use a relational database that will already guarantee atomicity for you, but if I were doing that, then you just use a library to guarantee atomicity, and that's it. But in here, we were trying to learn how to do this. It's actually like the last man resort. If I don't have like the ultimate tool, but I want to construct that by myself, how do I achieve this? Then that is actually what this lecture today is about. And similar to the other one, we're still talking about how then we might solve the problem. So the problem is that once we know that there is a region of the code that has problems, then we're circumscribing the area of the code that has the problem, and then we apply like a security protocol. We'll never tire to say that most of you, even in the coursework, are just protecting the variable, not an entire region. Thus, then you have race conditions, and even though you're thinking that your code is working properly, it's just because maybe you're hitting run one time, it works, you're satisfied, and then you continue, but then I'm going to run like 10,000 of times the code, and suddenly I will see a race condition. So it's not because one time it went smoothly that everything is perfect. So you need to identify the region where you have mutual interdependencies between updaters over variables, because for example, you could think about what if I'm updating some kind of internal state, and then depending on this variable that I'm updating another one, then I need to enforce that all the updates are atomic, so done in one shot across all the variables that I'm updating all along. So the idea is that it's like it should be zero. So that is actually the thing that I could say. This region should be executed by at most one process. Then we are going to relax that this afternoon with showing how the locks for restrict two-phase locking could be implemented. And without interruption, so to achieve mutual exclusion. As a rule of thumb, each region of code accessing shared variables in writing should be considered as a critical section, and that is actually what I was referring to beforehand. And this is actually giving you also an example. Another very common problem or mistake from students is that whenever we're creating a lock, they're creating for thread 1, for this method executed by one thread, they're creating in here new lock, then they're using the lock and unlocking, creating another lock in here, and then unlocking in here. But you see, I have two methods on which I'm updating the same global variable. And if I'm doing that, then I'm knocking nothing at all. because I'm creating a new object that is going to arbitrate the access not to the region, but is actually bounded to the lock itself. So it's not because you're declaring a new variable that this variable that you're newly declaring in here with a new object is going to magically, as you're accustomed now with AI most of the time, happen also in the second slot. So you need to say to the machine, this is actually needs to be safeguarded in the same way. And how do you achieve that? By declaring one global variable within the main class, or yes, like a static in there. So only if you're guaranteeing that the object is actually the same, so like the same lock, you're going to guarantee that the same method is going to be safeguarded. And then you're requiring that the update of the variable is done once. So this is actually a very concrete and short example of where, okay, I just have a variable that I'm updating in 2 points, and what if I have 2 threads running the same method to the 2 methods at the same time? So I need to safeguard both regions with the same lock. So that is going to be important. So if you're going to run the code, then you'd see that all the problems that you'd have by updating this variable. So one update might overshadow another update and things of the like. So you're not necessarily having like the algebraic sum of the values that you're reading in there. So maybe you are losing one of the updates with a right conflict. And this is actually the thing. So the idea would be that there might be regions of the code of the method which are not critical sections. For example, you're declaring a variable in there, and within this critical section, so within these regions, you're just running within the thread itself, because they're not global variables. And that is also another problem, because you didn't see also properly how a programming language needs to be used. So let me get that straight. If we're going back to the first lesson, just for a refresher, whenever you're doing a method call or a function call, then all the variables are going to be, all the variables within the method, declared inside the method, are going to be within the stack as a rule of thumb. Then, so they are local to the thread itself. While you have other variables that are not associated to the method execution, that are, for example, of the class itself where the method is run, then those are going to be global. But anyhow, if you're declaring like a local variable to the method that is going to be executed, that variable itself declared there, or any object instantiated there, then it's not going to be shared across the other objects. Therefore, that's why I'm saying there might be also a region of the code which is non-critical section by itself, because I'm just doing something local. Like, for example, if I want to return a value to my caller, and then in here I have a critical section, I can freely assume that I have a variable declaration, and then you're returning the value afterwards. So that's why even in the code base that you've seen, you might see like type of a field, return, then to do field is part, allegedly that should be like the space for a critical section, and then you have the value that you're returning outside of the critical section. But that is actually guarded because basically you have just your local copy, so you're not passing outside a global variable. And then you have some properties. So now you've seen the problems. So now we see the properties that we want to guarantee in order to make the execution correct. So then whatever I'm saying this is very actually high level. So you cannot claim that this is actually theoretical, because you also have scientific literature for safety, aliveness. You have how to define a concurrent program. You're not seeing anything of those. So just the mainly definition of these properties, so you know what they are doing, but nothing more. Just something very applied. Therefore, you have 2 properties independently from the multi-threadedness, even if you have like a concurrent program or a sequential program. Either way. You have safety guarantees, which is nothing bad happens. That is, if the program continues to run, then it never makes wrong actions. As a rule of thumb, that is actually the thing that happens whenever you're doing testing. So whenever you're doing some kind of testing, you are testing for this. So you're checking whether at any point where you're executing a method that is returning the value that you're expecting. So you're checking about its safety or correctness somehow. But that could also be transferred to a multi-threaded computation, that's for sure. So if you have, for example, multiple threads accessing the same resources, so you don't have race conditions while accessing the data. So that could be like a safety property, and then it's instantiated to what is the bad thing. So for the concurrency reasons, then that bad part is actually race condition. So you would need to guarantee that no race condition occurs. And then such property can be ensured by synchronization mechanism, that's for sure. You're having basically a critical section which is protected by a mutual exclusion using locks. Then I know that even the literature is quite confusing because you have mutexes, mutual exclusions, locks, and then you have, I try to disambiguate as much as possible in here by providing unique terminology. So mutexes or locks are synonyms if you're using any other programming language, but in here I'm trying to use as much as possible the terminology of lock to refer to the object that you're using to guard, region, and mutual exclusion to refer to the property that in that region of code guaranteeing that only at most one process should access a critical section, and the critical section is the region of code bounded by the locks. So liveness is also something relevant, but we'll see that later on in this slide more precisely. And mainly the discussion of today is going to be related to liveness. Something good eventually happens. So that is actually related to the blocks that I was already telling to some of you. So I want to avoid blocks, and then it still is live, so it continues to compute something. So it's not waiting for resources, it's actually not waiting for anything else. This entails that synchronization mechanism shall not prevent the termination of the program. A process cannot wait indefinitely before being able to access a shared resource. At this stage, you might have seen that if you have did this exercise from this, in which I'm actually showing that what if you're using both a shared and an exclusive lock to guard one specific variable, then you're locking itself the thread in, because just at commit time that all the locks are going to be released. And then another common error in exam is actually that you are releasing the lock in here before the application of exclusive lock, because you're saying, hey, but actually you're accessing the same variable, and so that is actually what it makes sense. Then, but the exercise is not about your ideal protocol, it's about restrictive phase locking, which is the title of this, and the restrictive phase locking requires that all the locks are unlocked at the end. So no matter how fantastic your protocol is for you, but that is actually not doing what the exercise is requesting you. So that was an example. So if I'm holding the lock until the end and I'm trying to acquire both a shared and exclusive lock, even for the same thread, I'm going to have like the thing that we're going to see as a deadlock, because then the computation will not progress further. And so that is an example of an indefinite wait. And then we're starting to see mutual exclusion, deadlock, free, and starvation in more detail, which are the properties that are trying to be guaranteed. So we're trying to achieve mutual exclusion. So a region of the code is going to be actually only accessed by one thread. We want to have a deadlock, which is indefinitive wait, or starvation, which is a relaxation of the former, for which one thread is actually waiting indefinitely, but we know that eventually it might be able to get there, but not soon. And that also boils down somehow to absence of unnecessary delays, but that is more of an optimization, so that is not going to be covered. And you have just a paragraph in here, which is a process is trying to enter its critical section, and the other processes are executing the non-critical section or have terminated. The first process is not prevented from entering its critical section. So this is what an absence of unnecessary delays is, but is a subtlety if compared to what is starvation-free. So we're just to look at the coarse-grained definition of starvation, which somehow is similar to that to some extent. So before we start discussing in detail mutual exclusion, deadlock, and starvation, do you have any questions? Okay. So with mutual exclusion, we say that a resource is accessed in a mutually exclusive way if, at each instance of time, the resource is accessed by at most one thread. So, as I already told to some of you, you have two processes and they're trying to print something on the printer. And let's suppose that you have like in the USB, that you have a shared printer, and then two computers are trying to send a printing job. And let's suppose that the driver of the printer is actually badly designed. So it's not printing one document at a time, but as soon as I have the data, it's going to print itself. So you'd have one document being the merge of the two documents, and that is actually something that you want to prevent somehow. So you need to create, for example, a queue or a mechanism to guarantee that only one task at the time is executed, so you're creating a queue. But also the queue is concurrently accessed, so you need to guarantee that you have a mutual exclusion to the queue itself when you're providing the document. So then you need to guarantee that the printer resource is accessed only one at a time, and then the printer itself will just use the queue to print each document separately. And therefore, that is just a concrete use case example. If you go to computer science, that boils down to have a producer and a consumer, one giving the information and the other one taking the information and digesting it somehow. And that is also called, for example, a shared buffer. That is an example of data structure acting as a printer. And then you have two processes that need to update a shared variable. So that is actually also related to that, so not necessarily related to a queue, but the generalization of those, on which basically you could do an increment. Then let's go into detail into something which is different. So, end of part 1, part 2, deadlock problem. Then the deadlock problem happens for multiple use case scenarios for which you have a depiction in here. So in real life, you have like cars and they're trying to go beyond the crossroads, but everyone arrived at the same time, and so you don't have a way to say who shall go first. Everyone is stubborn, no one decides to do a step backward, or no one is too brave to go and start doing, no, please after you, no, please after you, no, please after you, and then you have a deadlock. And that is actually what happened. Actually, what some operative systems are going to do, very simplistically, is like you're having like a loop in a graph, similarly that you might have in here. So the operating system might decide to just cut one thread off and make the other one access the resource. So if you have any kind of deadlock, some operating systems, not everyone, will do that, some other will just wait indefinitely. Another use case example is you have two persons, one trying to do some omelets and the other one trying to do a pancake. For doing those, then you need two resources. One is actually the pancake and the other one is the olive oil. So just to make it reflect in here, we're sharing one resource, and therefore, which is actually the crossroads, and therefore you have a deadlock. In here, you have also deadlock when sharing two resources, not necessarily one. So I'm showing you a more complicated example of a deadlock. So they want to make their stuff, but both, in order to make the final product, like the computation of the process, you need both a pan and an olive oil. And so, for example, Adam is grabbing the pen, Amy is actually grabbing the olive oil, and no one is actually willing to release the resource that they are holding. As a consequence, you have a deadlock, because actually no one will cede the resource which is actually required to compute and to progress with the computation. So then we need to guarantee the program to be deadlock free. So, but we don't have this kind of weights. Then this is actually the light-hearted description. In here on the left, you have everything with resource 1, resource 2, which is R1, R2, process 1 and process 2, which are P1 and P2. So you have everything but in a more abstracted way, but it's just an abstraction over the examples that I was providing now. Any questions regarding the notion of deadlock or the examples precisely, or how that could be related to threads? All clear? Good. And then you have the other example about starvation. So in here you have like one obnoxious thread which is trying to get all the ice cream by its own, or maybe it's taking too much time to give money to the person, and therefore is making all the other kids in the queue starve somehow. Because maybe you have a priority queue and this and therefore you're getting the priority or somehow, and so you create starvation. So the thing that you're having is one process might lag the access to the resource due to high priority or due to the induced priority. So maybe you're not prioritizing the thread itself, but you're making the code so one thread is prioritarial if compared to the other ones which are lagging behind. And therefore, so in here, the solution is not to make those also the priority queue, because then you're still making weights. The solution is to actually make a better design of the program itself. And so another example might be also the other way around. So not only necessarily one process blocking everything, but you might also have like a fast succession of threads, and you have one thread in the opposite situation, which is always lagging behind. That could also create starvation on the other way around. So you have a resource, and you have three processes, P1, P2, and P3, which are periodically accessing the same resource. And you have P1 and P2 rapidly accessing something, and then you know that P3 is actually lagging behind and will be very unlikely to access resource R. So then you need to either design the algorithm better or to but it's the only thing to do. Because actually increasing the priority will not make the solution. Maybe the problem is just how you implemented your code itself. So you have the two different examples. So the other important thing is actually that deadlock implies starvation, but not vice versa. Why? Because deadlock implies starvation, because if I'm stuck forever, then that implies that I'm starving because, and P3, as in the prior example, is not going to continue, but that is not true in the vice versa. So if you have starvation, you don't necessarily have deadlock, because it's not because P3 is very slow at obtaining the resource. Maybe if you have a very good algorithm, eventually the situation will be unlocked, and then P3 will be able to obtain the resource. So these two scenarios are going to be different. As I'm also showing through the examples, in here you have either too much politeness or too much amount of stubbornness, and both are actually causing the deadlock issues because you have resources that are not released. In the other scenario, you have like either a fast succession or a resource detaining the resource by itself. Either way, you have like a prolonged waiting, which feels unnecessary. And then when this prolonged wait becomes indefinite, then you have a deadlock. But the difference between the two lies on the logical definition of a program. So only if you're analyzing the code, then you know whether you have starvation or deadlock, basically. But from the perception that you have from the outside, you have just an indefinite time. And then you need an infinite amount of time to determine what this situation is. So that is just a clear refinement again. Please remember that critical sections are just regions of code that might exhibit race conditions. Because there is actually, so that's why some of you asked, actually, are there any kind of good YouTube videos? So sometimes the terminology might be, ambiguous. And the terminology that we're going to use here is try to be like less ambiguous as possible by identifying precise terminology. So you might risk that another person might use the terminology differently. And in here, even in the literature, you have some kind of ambiguity, but it's clear from the context. In here, I try to use like unique names all along. So it's fine that you are using additional material, but please be aware of the issues that might be there. So, as we'll see, we might see here locks or Decker or Dijkstra algorithms or Peterson ones as a way to solve this kind of contentions and so having the limitation of mutual exclusions. And definitely we're going to look at Decker, Dijkstra, and Peterson's algorithm at the end, but if that is going to be covered by the exam, yes, and you need to just understand the idea, not the technical details on how they are achieving the solution. That is going to be discussed on the last lesson on Monday, or any kind of later occurrence. Still, with two L's, not all of the possible solutions implementing mutual exclusions guarantee such good desired properties. So that's why you have solutions that are achieving mutual exclusions, but not necessarily fairness, starvation, or being deadlock free. So maybe you are simply achieving mutual exclusion because you're just allowing one process to run that region of code and you're blocking everyone out, and those are in a deadlock. Or you are creating a starvation, so through which you are guaranteeing mutual exclusion, but then you're not having the good properties in here. So that is also goes with how you're argumenting something. So you could also say that you're achieving mutual exclusion, yet I have a sequential program, so trivially you have like a program executing mutual exclusion properties, but then if you're not safeguarding your program with mutual exclusion, then it's not going to entail that you have concurrency issues. So before we start, see some features. Do you have questions before we? Yes.
If we go back to a slide deadlock problem.
Yeah.
Yes. Does oil and pan is shared variables?
Yes, correct. And as an example, on the top, the shared variable is the crossroad in terms of access to, so you could see the crossroad as not only accessing the crossroad, but also able to reach your destination. So it's the combination of both, so the combined provision. And here, both elements are a resource, correct. So you could have deadlock by either a problem with one single resource, or whenever you have like a mutual dependency across resources. And so one is obtaining one resource, but in order to compute the rest of the computation, you need access to the other resource, but that you have like a triangulation on which the other process is holding the opposite resource, which is required by the other one to continue, and vice versa. So like a vicious circle. Does that answer the question? Okay. Any other question? Yes.
So, in one of the later slides you mentioned that deadlock implies starvation.
Yep.
And on the starvation slide it says that if you have P1, P2, P3, and P3 is the one that is starved, P1 and P2 are working fine in this example.
The thing is unlikely but not impossible.
So, in the next slide when you say deadlock implies starvation, does it mean that it's talking about a more strict form of starvation where all P1, P2 and P3 are kind of starved?
Not necessarily. So that is just referring to any process or any thread, really. So you have starvation or you have deadlock. Those are just examples. The formal definition, if at least one thread exhibits starvation, if at least one thread exhibits deadlock. So you require at least one thread to have a problem. Then, why do I say that deadlock implies starvation but not vice versa? Because deadlock implies starvation because for deadlock you will never obtain the access to the resource, and the definition of starvation is that it becomes rather unlikely but not impossible. So, you are falling on the rather unlikely. So you are rather unlikely to do so. But the opposite does not hold, because if you could have a possibility of accessing that just after a prolonged amount of time, which feels like an unnecessary wait, nevertheless, you are not necessarily on deadlock, because you might have the guarantee that eventually you might access to the resource. Does that answer the question? Okay. Any other question? Also, another thing is going to be that, please, whenever I'm going to release the after Monday, the questionnaire on Google, Google Forms, which are the topic that you haven't understood, please do not click on all the topics, because then that entails that everything should be like repeated, and the major part is which topic you understood the least, because I'm going to pick basically the topics from the list given like the majority vote. So if all the topics are going to be equal, then I don't know what to choose. So if I have like a differentiation, then I know which topic then needs to be picked in order to be analyzed. Then I'm going to discuss busy waiting and test and set, and then I'm going to give you a break, that's for sure. Then, with busy waiting, you have not necessarily a way to arbitrate the access, but that could also be used in conjunction with another way to arbitrate the access. This might be the following. So you know that, for example, you're waiting for a file to be read, and maybe it takes some gigabytes, or maybe you're downloading a file, which is actually taking ages. So the thing that you could do is actually tell the scheduler, as we were seeing yesterday, that you are not doing too much. So the resource in here is actually the CPU, and if there is actually something better or with a higher priority to run, then please give it the opportunity of run on my behalf. So with yield, which is different from Python's yield, you're going to say, okay, I don't need to use it, and then maybe we are busy waiting, as we're going to see later on. So I might have like a while true condition or a while condition, for which, actually a while condition, or if the condition still holds, then I need to wait. So instead of losing the CPU cycles, doing nothing at all, you just provide a hint to the scheduler saying, okay, I'm just going around in circles because I'm waiting for this condition, just to return the scheduler time to another process actually doing something useful. And then I could also use the yield. It's just a hint, but it's not required that the Java virtual machine will actually use it. And in fact, we're trying to avoid as much as possible busy waiting solutions, but at a very low level, for example, at the operating system level, that is what you're having. So that's why I'm saying you might have a while condition, or you could also say while the condition happens, then do thread yield. So why it's called busy waiting, by just doing like the sentence and word analogy. I'm busy because I'm continuously checking the condition, but I'm not doing something productive in my computation. And so nothing is changed actually, and so I'm waiting for the condition to change. So that's why you're busy, but still you're waiting for something. So and then thing is actually, it's better to use a hardware mechanism suspending the active process and allowing the process to run, which is usually done through test and sets. So as I was saying, if you're accustomed with low-level programming like operating system level, then you have this kind of test and set on which you might have like a CPU register, a memory address, and a value. And then you're trying, but you're not as low level in Java. So maybe the Java virtual machine implementation, you are reusing hardware-specific implementations, but given that you didn't do like an operating system model, we're not going to see that in detail. So you're trying to check the assignments, and then you have from the CPU that the assignment operation, so the write or assignment is atomic. So given that and the test of a condition is atomic, then you're trying to implement like a critical section through a test set, as we might see later on. So you might retrieve the value from the CPU and then restoring the value. And the thing is, can we also do that in Java? Can we mimic that? Yes, we can mimic that, but in a software-related way, which is going to use busy waiting underneath. So that's why I'm not using explicitly hardware solution. So if you're seeing the older slides, you might see that the test and set is a hardware solution. But it's a hardware solution only if you're using hardware primitives. In Java, if you're using a test and set, you cannot use directly hardware primitives for which you have scheduler-based, which might use hardware-related. So that's why I removed the prior terminology and differentiation between software-based and hardware-based. So in here, the test and set is actually software-based. Because you could implement one, but still you can do that only with busy waiting. So how that is done, that is actually a first implementation of a lock, which is still a non-efficient one. And as always, you have the implementation of these classes on the slides package in the code base being provided on campus or available on GitHub. So through busy waiting, I could implement a lock in the following way. I have an atomic state, which is just my global variable. And with a lock, the thing that I'm trying to say is I'm trying to get the value and is set it to true. So the thing that would happen, given that, so you see the problem is that the get and the set are perceived as atomic operations. So that's why this kind of implementation works. Otherwise, if they were non-atomic, then the implementation might have been wrong. So the first process sees the state variable as being false. So given that that is actually false, then I'm breaking from a while loop, and then I'm allowed to continue the computation. The next, any other process that will try to invoke lock will see the global state variable as being true, and so it's going to loop indefinitely in the while loop. If you want, you could also add a thread yield in order to save CPU clocks. And then you know that you could only go out of this while true loop if someone is invoking unlock. So you're releasing the mutual exclusion region, and then, given that you're doing an atomic state operation by setting the value to false, then the other process, any other process waiting on that, will be allowed to continue. And what is actually the thing? So what if you have two threads actually trying to invoke lock and try to access the mutual exclusion region? Will that create a concurrency issue in terms of race condition? Well, not. Why? Because the get and set is ensured to be atomic itself. So I'm not creating race conditions only for that reason, okay? So I'm ensuring that only one thread will invoke the method and set back the value to... So getting the value and setting that back to true. So only one value will retrieve the false value that the second thread is setting and will set that back to true. So the other thread, which is going to be the second one, so while the first will be allowed to go inside the critical section, the second one will not be allowed because it will invoke, due to force majeure, the get and set method next, and then is going to get the value, and the value is going to be true, and is trying to set a value which is also true, and as a consequence, is going to also wait indefinitely while the other process is going to go inside the critical section. And that is actually what is explained in here. And then if you need additional reference of this kind of implementation, you also have a reference for the book. But this is just for this other part. The other part of the book is quite different from the thing that we're discussing in this module, so you don't have a lot of information regarding the rest, unfortunately. So I just do this example from the book. Then the idea is that the Dicker and Dijkstra and the Peterson algorithm are actually refinements of a testing set in order to do more whenever you don't have necessarily atomic primitives like a testing set operation at the hardware level, or whether you don't have like an atomic boolean, like in this scenario. So before the break, do you have questions regarding like understanding of that? Oh, before I ask for questions, the other important thing that also gives you the notion why it's actually very important to always lock and release the lock. Because if you're never releasing the lock, then you're always going to trap everyone outside and you create a deadlock. So whenever you're making one process accessing the critical section, then it's also required to release the lock. So you also give the opportunity to other threads to access that. Yeah, so now, besides that, do you have questions? Then, if not, I'm going to give you like 10 minutes break and we're going to continue at 33. Yeah, hello.
You're here.
Okay.
You said I need to implement my ID.
Yes, please.
I did. Does it start with letter?
Anyway, it's fine. That is also good.
And whenever I finish from a to-do, thing.
Yeah,
Should I remove this comment or leave it as it is?
completely up to you. So, but it's just for you as an indication what needs to be done. If it's actually clearer to you that you've done it, that's okay. And nevertheless, we're not going to change the marking depending on the comments. We're just going to run the scripts and check whether that is going to be done in this way.
Okay, and yes, and when I tried to do the scoring thing in the
Yeah.
testing, it didn't work. As you can see, when I go down, yeah, that's what happened.
Because there was some kind of because you killed the thread. So the thing that happened is that actually something went to deadlock, and there should be like a waiting time, as far as I'm concerned. So I think that you maybe just kill the process, like now that you have a code of 130. So for that you don't have any kind of score because actually it's going to deadlock. Anyway, if you're going to testing, you will have like a waiting time associated with that. So really depends on where that is going to be blocked. Yeah, you have a waiting condition, present variables, so you could do it this way, and then doing this you shall be able to see moderator join. Moderator join. So the thing is that is happening is that you have this process and you have that is not even terminating at all. So and then the problem is that this process is trying to wait for the moderator to finish its execution, but given that nothing is happening, then it's just waiting indefinitely. So if you want, but how many times I'm doing this kind of operation? I'm doing that 200 times, so in there, if you want, you could do something like... You should also have like a join with a duration in seconds. So if you want, for the time being, you could also say duration. Nope. No problem. Duration of milliseconds, for example, we say for the time being after 7 seconds, just by different key. Yeah. And then that should continue. So the issue was the duration of seconds, you could also say after 7 seconds or something. So if you're doing this, you're going to force all the wait to be stopped after 7 seconds. Then if you have like an actual implementation, why is that saying that cannot be converted into long? What if I'm just saying 7 of long? Why on earth? Long? Okay, is a duration representing a number in milliseconds. Duration? And that requires duration. Why is it not telling you this? Quite weird. Duration of seconds. I think that because I think there is a mismatch between your API and is expecting this. You're expecting just a milliseconds in here. Yeah. There is actually a mismatch between the library that you are running underneath and the code that you're seeing. So the ID was So now everything should wait after 7 milliseconds. So 7 seconds. And now if we're just saying in here I'm doing 1 after 1 millisecond, and then if it's not doing nothing at all, just continuing. Yeah. So now it's just waiting for 1 millisecond, but please be warned that that is not going to be like the thing that we are going to mark, because actually we're going to do an indefinite wait. So on our behalf, so now it's just to get you running and to get all the errors, basically. But we are going to do like without the milliseconds being specified. So then how we're going to mark that, we're going to stop the computation and isolate the blocks, and we're going to say, okay, that was that block, and so we're going somehow to downmark the part related to that, and we're going to continue with other tests. So that's why it's provided there in a script. So if that is creating an issue, then we're going just to, then you see, now it's continuing to do all the tests. But that is actually what it's going to look like.
Yeah, but the scoring is not going to show, right?
Yeah, it's not going to show, but now it's going to show. After a huge time, but because he's running all the tests, but now it's going to show.
Whenever I submit the coursework, I should remove this millisecond.
We're going to use our script nevertheless, so we're never going to use that.
This is for us then?
Yes, exactly. And we have our local code, because the student could also have extended or changed the code, so we have our tests.
Okay, I just want to ask you about you said there's like the 50 grades?
Yeah.
Which is like the thing, you don't have to have background in concurrency?
Yes.
I was trying to find it out here.
Windows, I suppose. Yeah, by the way, yeah. Okay, so now we should break.
Yeah.
Sorry, you were saying?
Yeah. This is the bug. Okay. The thing that is that has no, we don't have to have background and concurrency while doing it is something like this one.
No, actually everything. Because the thing is that at this stage we are. So the idea is, what if you're not using blocks at the time being? If you're not using blocks or implementing the monitor, as we're going to discuss this afternoon, then you could also fill in all the methods that you see here, everything, without the use of any kind of concurrency issue. And by doing that, you're just checking whether the testing 3 is compliant, and whether that runs as expected. And given that, then you are ensuring that the program is logically correct in terms of the output that you're providing. Then on top of this, you're also adding like monitors or anything of the like.
Yeah, okay. Let's say, for example, this one generate new topic ID. this is might be simple, but this one, create new topic thread. Does that mean I should like implement this method too?
Yes.
Yeah.
Yeah. So because actually in here you see I provided maybe the way to update the ID, and you have this kind of create new topic ID.
Yeah.
So the create new topic ID might be related to this.
Yeah.
So you might use these two methods to use that somehow.
Yeah, and here I should like create a new thread. Is that what you
No. Thread is just like a blog thread.
Yeah, but topic thread is
Node thread is in Java thread. Topic thread from a blog.
oh, okay.
So a thread is going to call create new topic thread. But in here you are not going to create a thread like a Java thread, but a thread topic having a name.
Yeah.
Like a Reddit question. This
Like
kind
a
of stuff.
title.
Yes, the title.
Okay, thank you.
No worries at all. Yeah, question.
Just a quick one.
That's fine, that's fine.
So I had a bit of a brainwave last night and had a look at the locks. So, and one thing is what I noticed in your code, when you had to keep, I noticed you had two that said to remove.
But yeah, anyway.
So I was like, alright, that might...
You know, it was just for me to remember to remove it, but I didn't
Yeah.
remove them, and so... Anyway.
Right, yeah, and then I realised I was trying to use them, and then so I've been looking into locks.
No, that is old school. No.
This is, that's why, this is what I mean, this is what I'm asking, like what I'm trying to fix.
Oh, that's bad as
So,
hell.
with the lock,
No.
with the lock though, with it,
No.
but my question
Yeah.
is that I seen that's the old way to do it.
Yeah.
How would you approach it a different way? Because when I've been looking into the slides, this is the only way I can kind of manage it at the minute.
Yeah.
And I'm getting some feedback saying it's doing things right.
Yeah.
But I'm struggling to find a different way to do that. at the
Yeah,
minute.
because actually the problem with that synchronized
Yeah.
is that you are... So that's why it was already meant to be there in the slides.
'Cause I've got
You
two.
removed that,
Yeah.
but the thing that was removed was the read and write monitor.
Okay. So
That
just
is
use
good.
that instead.
Yes.
Right, okay,
So
'cause-
then, anyhow, given that that is working at the minute
Yeah.
with that,
Yeah.
so you have an understanding how to do.
Yeah.
But please, that is going to be
Use the
also
read
part
and
of the
write.
marking. Yes.
Yeah, because when I was doing it and looking at the slides, and the synchronise was the only way was kind of I was finding at the
Oh.
minute.
Oh,
At the minute.
You also have a lock.
Yeah.
That is going to be discussed now.
Okay, right. So,
So-
that's just that next bit. Yeah, because that was the only way, and everywhere I looked online was saying this is an old way. So I was like going, okay, what's the right, right approach then? You know what I mean?
Extending read and write monitor.
I get you now.
Because that,
Yeah.
as I was discussing yesterday, is going to use both waiting for an event
Yeah.
and getting or setting values within the topic thread.
Right, okay, I get you. Yeah, because it was like it was throwing me down one way, and then I was like, I'm sure I'm supposed to go this way because I found I wasn't using this.
I know. So that's why I
Yeah.
kept the over variables.
Right.
Otherwise, I would have also expected students to do
Well,
something.
I'm glad you spotted this straight away because it was immediately my question why I was like didn't know what to do besides it. You
Yeah,
know what I mean?
also then we're going to discuss this in this afternoon, but the issue is going to be that with this way, you cannot have multiple waiting queues for multiple conditions.
Right.
While, for example, for a read and write monitor,
You
ensuring, for example, strict
Yeah.
two-phase locking, then you need to have multiple queues.
Okay.
One for the threads waiting on read and the other one waiting for write.
Yeah.
So if you don't have that in the old way,
Yeah.
you are forced to wake
Single
all the
thread.
processes up,
Yeah.
check for the condition,
Yeah.
and then remake them and wait the ones that are
So you're not using the multi-thread and RAID. Right.
No, nowadays no.
Yeah. Because they were saying online, it was saying that this is the old way to do it. I wouldn't recommend it, but I couldn't really find a different approach just yet. You know what I mean?
The thing is that you have is actually, if you're going to the slides for monitors,
Yes, give me 2 seconds.
so that's why I was providing that at the very beginning.
Which one, sorry?
Monitors,
Monitor.
so that's why I think you haven't seen this. So
I
if
don't
you
think
go
I've got
back,
to this one yet.
Recap. Ah, yeah, that's why we're not seeing that because that is Java Objects Monitor. That is
Okay.
the thing that you're using.
Right.
Please go down. That is the thing that you're using.
Yep.
We're using wait notify eventually.
Yeah.
Semantics of wait and notify.
Yep.
Go forward again. Please go up in this way, basically, or either we synchronized or using object as a monitor. So basically, whenever you have
Yeah.
lock
Okay.
synchronized on the object is like having synchronized over this.
Yeah.
So if you're having just one object, which is the bounded buffer, and you're doing the synchronized over this is actually what you're achieving.
Yeah.
Basically, the thing that you did is redundant,
Yeah.
because you could also have used the same bounded buffer object as this, as
Yeah.
the lock, and that is actually also equivalent of using synchronized, which is just syntactic sugar,
Yeah.
and then using the waiting condition as such.
Yeah.
And the problem is then you're not able to do this. So in here you need to do busy waiting and check whether the condition is always true. While in the other way, as we're going to see down below, then you're only going to wait the processes when the condition now holds.
So it's waiting and waiting for things to finish and waiting for things to process, and then it activates what it needs to do.
Yeah, so it's just activating some processes just associated to the waiting condition.
Yeah.
So that is just one for, let's see, reader and writer's problem. Do you have the other? That is just for that. So you are signaling depending on one specific condition,
Yeah,
and
what's
you're
happening.
waiting on one specific condition.
And once it's monitoring the lock, and once it's done, it'll read the signal and then unlock it.
Yeah.
Right, I get you.
And
So,
just not waking everyone up, just the one waiting for that specific
yeah, so
condition.
that's
for
more
example.
efficient and sort of.
Yeah.
Right, that makes sense. I can rework that.
No worries at all. Take your time. Just now you have a preliminary solution, and then when you have more time.
Brill.
Yeah, no worries. Yeah, question?
My question is, in this two-phase lock,
Yeah.
it means multiple threads can have read lock.
Yeah. Read. Yes.
But only one thread can have write lock.
Yeah.
Oh,
Yeah.
so, but I mean, in here, here, I think not in this situation, you didn't need the lock B.
You cannot trust ChatGPT for doing concurrency.
Okay. Okay.
Let me clarify now. So please do not use ChatGPT for ensuring whether a program is correct. In theory, in the theoretical setup, you have something called the holding problem. The holding problem in logic tells that a computer program cannot check whether another program is correct or not, like a Turing complete program. So if you're asking ChatGPT, it's going to yield to a solution which is not correct. So I wanted to say that to everyone, so to avoid confusion. So please trust the protocols that I was talking about. And yeah.
No, I mean just this logic. If you have
No. That is not strict two-phase locking anyhow. So I'm asking you to do an exercise on strict two-phase locking, and that is not strict two-phase locking.
it's not straight.
No.
Okay.
No, it's not strict two-phase locking. You have the exercise. That is the thing that I said. You need to abide by the exercise,
Okay.
not invent your own protocol. And the other thing is that the strict two-phase locking exercise is abiding precisely to the topic that you have in here, which is this one. You have a protocol, which is this one. This is the way to achieve this. And the other thing is why I'm not saying, okay, whatever the solution will be correct, because then otherwise I'm not checking whether you're automating something or if you're using your brain. So in order to check that you're using your brain to achieve a solution, I'm asking you to run an algorithm. Otherwise, I know that you have a lot of ways to actually do something that might be equivalent somehow, so you could also lock everything out, and then you're doing something, you're avoiding racing conditions, but the exercise is precisely on the knowledge and understanding of the strict two-phase locking. So that is actually what I said from the very beginning of the module. If you're doing another solution which is still concurrency free but is not abiding by the strict two-phase locking, then the solution is not going to be correct. That is what the protocol is about. Then in your coursework you are free to use a protocol which is not necessarily strict-to-phase locking, you could also ask ChatGPT to create your program. But you might be warned that you have something called in logic, which is called the holding problem, for which you cannot trust a machine to check whether another program is correct or not. So that's why you have basically hackers trying to attack machines, because they have limited access or information of what is happening, and they are very easily gullible machines nowadays. So, besides that, I think that we also asked most of the question during the break. So, if you have any other question, please ask them in the afternoon, please. So, software solutions were already covered before, and now we're trying to use scheduler-based solutions. So now we're introducing scheduler-based solutions, and we're just doing a brief recap on software solutions. So these solutions, as I was saying before, are not efficient and should never be used in practice. So we want to use as much as possible the primitives that the language is giving us in order to be efficient. So the critical sections, how to do that via locks. So we want to access basically whatever the implementation is down there under the assumption that the locks are going to use, hardware-based solutions for which we might achieve better efficiency. I forgot the microphone. So we want to use those. And then when it's actually finished to access the shared objects, the thing that we want to do is basically leave a critical section, otherwise it will create a deadlock. The algorithm and state variables used to ensure mutual exclusion can be encapsulated inside a lock class. And that is actually where all the logic control will reside, inside the lock class that we're going to discuss now. Thus, we can associate a critical section with a lock object that encapsulates a particular solution to the problem. And that is what we're trying to do. So we are going to reduce the check to a limited part, which is while invoking the lock or a lock execution. Therefore, we associate each shared object with a corresponding instance of a lock object. And processes wishing to access the shared object must invoke the appropriate operations on its lock object. But what are those about? What I'm blabbering about? This is actually a practical example. Okay? You have an object in there which might be created. In here, I'm just providing like a simplistic way. So I'm either creating and having basically an object which is within the method, and through that I'm ensuring locality only for that runner, or only for this region of code, that I'm locking something in. But as I was saying, then if you have, so you cannot have necessarily here a new, an allocation of a new thing, because otherwise you're not ensuring mutual exclusion, because you're creating a new object all the time. So it might come from somewhere else. In here, I'm just saying that I have a variable called object somewhere in the code. And then, when I have a critical section region that I want to protect, I'm using just a traditional Java object to lock and unlock something. So the thing that you're doing is basically using this kind of lock and unlock. So the thing is still that is just guaranteeing the synchronicity or the atomicity of the operations that you're doing inside, but it's not ensuring the global correctness of your code. And the reason is that then you need to protect also the other regions of the code in order to ensure atomicity of the operations. So you need to ensure not only that in that method, but across all the positions, you are achieving atomicity. So that boils down to the thing that I was discussing from the very beginning on this slide. So in here, I'm accessing the same global variable. It doesn't make any sense if I create just one lock in here, or one lock in here, or creating two locks and new in here. The lock needs to be shared in order to ensure atomicity, or to avoid race conditions on the global variable. So that is actually what that part was blabbering about. By the way, you have that was like the old school way, and then you have the new Java way, which has better safety guarantees. So one of the things is why it is reentrant. We're going to see that later on. But one of the reasons is the same thread could invoke potentially like a recursive method call, and then if you are locking all the time, the thread also could lock itself in the recursive method call. So in order to avoid that, then you're going to use reentrant locks, but you're using better guarantees also in terms of not locking yourself in a recursive call of your own method. So that is why it's called reentrant. So you have new things. It's like trying to use beginning of a century car when you have better cars that are more efficient in all the ways. So I'm trying to use something very old. And those are similar. Even in this scenario, you could guard a new lock, but even in here, I'm just providing the lock as in here, just to show that you have a variable declaration. You are not forced to declare the var inside the method. We're going to see plenty of examples where the reentrant lock is actually declared as a field of a class. And so it's going to be like a global variable, thus ensuring like atomic control across the class. And so in here you also have other implementations. So if you're going back to the older slides from the other professor, they were using like a pseudocode notation for the locks on which you needed to specify which process was locking in or out. In here, you have all the technicalities hinted by Java for you, because in Java you always have the thread name associated to whatever is performing, and therefore as a consequence, you already know who is performing the lock or unlock operation. So whenever you're going to see that a lock requires like an ID of a thread, that is just in an old implementation on which you have no assumption of what is actually Java doing under the hood. And then that will be clearer with the Peterson algorithm, but anyhow, you could freely assume that Java always knows who is calling itself and who is trying to lock or unlock. So you have like memory of whatever is happening. And the idea is the reentrant lock keeps the same monitor lock given by the synchronized keyword. So if you have read the slides, you have also read that, but this is actually the first time you're reading that, so that's fine. But it's just if you already encountered now there or someone telling you to use synchronized. And read and write locks for the first lecture actually implement a read and write protocol for strictly two-phase locking. So we're going to see this afternoon basically how to implement that using the reentrant locks. And the other part, which is actually sound, is why is actually best practice to do try and then finally, because you might also have like an exception which is thrown, and then by ensuring that the execution within the finally actually ensures that you're always unlocking something, even though something bad happens inside of here. Do you have better examples to show? The synchronize is actually just provided later on. So in here is just a caveat if you're also looking at the previous videos. So all material is actually assuming an implementation of locks through test and sets, referred to locks as software solution. Nevertheless, modern programming languages extend locks with thread waiting queues, thus requiring some kind of interactions with the scheduler. So that is just if you are also a caveat, if you're also seeing other documentation online, or if you are seeing other people telling something differently. So in here you have the disambiguation and what I am referring to. So in here for us is going to be like scheduler based. So we are going to disambiguate whether it is a software solution or a hardware solution to say that is actually a solution that is using the scheduler in terms of interaction. Therefore, I'm actually guaranteeing some kind of disambiguity depending on the version of Java or on this available feature that I have. And so what is actually the idea? The idea is this is actually the proper way to use something, you see. I have a private lock, ERB, which is going to be like a Reentrant lock. So you see, I'm not declaring ARB inside the method that I'm using. Otherwise, I will just create a new lock, and I will lock only this thread singularly, and I will not lock the others. So it's actually very important to use ERB outside. And then as a consequence, I might have, as I was saying before, some non-critical section of the code. And then I have a critical section, I'm trying to lock it, and then when everything is done, I'm doing the unlock. So even in the older days, they were not doing try and finally, but that has become like a good practice, because by doing that, you're also trying to ensure that everything will be unlocked, even though you have an exception thrown inside. So let's try to, whether something bad happens. Then we're going to go a bit back and to use like methodology which is more old school but straightforward to some extent. So synchronize also implements a mutually exclusive lock on a specified resource, which is going to be an object, like a traditional Java object. So it's going to be like the first lock that we see, not the Reentrant lock. In a Java, each object comes with an associated and implicit lock. That was the first lock that we see, which is this one. So in here, I'm just using an object, any kind of Java object, and from the design of the language, we already have each object with a concurrency access. So that is what I meant. Then, if you're using Reentrant locks, those are new and specifications. But synchronize is going to be used, the old version of that. And then synchronize could be used like as a syntactic sugar for the old lock mechanism. And that synchronized keyword could also appear in different ways. So you could also have, very simplistically enough, a synchronized method. In this way, you might have like a class, and you're declaring the method as being synchronized. And that is actually going to look like a syntactic sugar, so a shorthand writing, for using synchronized or using a lock within the method of the class itself. And so, using implicitly this as the object of a resource on which is actually acting as a lock. So going back and unraveling everything. With synchronized, you're using as a lock this object of a class, which, given that all the Java objects are locks, is going to act as a lock. Synchronized methods are synchronized with respect to this. That is actually the thing that I explained now. So those also is a simplistic solution if you want to ensure atomicity across all the methods of a class. So if we're going to the very first example that we see, which is this one, You could achieve then atomicity on global result if you're declaring both methods are synchronized. This is actually a straightforward thing to do. So you're ensuring that. However, it is still possible for unsynchronized code to interfere with synchronized code, because definitely if you are leaving out one method which is not synchronized, it could still interfere with the module exclusion. And so you could still change a variable while not ensuring that that variable is actually accessed only one time. Also, synchronized method calls to different objects can execute independently of each other. So what does that mean? It means that if I'm having two instances of the same class and both are using synchronized, given that the locks of the synchronization is on this, that this is going to be different, and so we're going to do synchronized for different objects. The only exception is, as we're going to see later on, is whether you have a static method. Then if you have a static method, then the synchronization is going to be on the class name dot class. And that is still an object in Java, so you have a static method, that is going to be your this. But still, it's not going to be a synchronization over this, just on the class object, not on the actual instance of a class. And definitely you could also represent the synchronized method with reentrant locks. So you need to create a new reentrant lock variable, you need to instantiate, and then you need to call lock at the beginning, and you need to call unlock before closing the method and returning the value. So I'm giving you an example of usage of synchronized, which is also available on the code. So what if I want to create a synchronized counter where all the operations are atomic? Then if I'm using synchronized, it would be very easy. I just put synchronized on top of all the methods, so I'm ensuring that I'm synchronizing over this. And then I'm ensuring that if you have two processes trying to get C and doing the incrementation, so only one of these operations will run at the same time, will run one at a time. So if one process is trying to increment and decrement and returning the variable, I will not allow this operation to run concurrently. Only one of these operations will be running. So that is actually what happens before relationship means. So whoever has the priority of running something first will run, and then afterwards you would have the output of this computation. So a good exercise for which the solution is also provided on the code base is to replace this synchronized with a reentrant lock by declaring that as a field of synchronized counter. So I'm restating that all the time, but I could also see courseworks where you have just the creation of reentrant lock within the method. So no matter how I'm providing that as an exercise, you still have students doing the opposite, so not the best practice, and creating the lock all the time. So you don't have any kind of concurrency control. Then I will just finish synchronized, and then I will ask for questions. So then you have something different that some of you are using, which is actually the synchronized statement. So a statement is not like using that as a keyword, you're using that within, how do you say, you're not using that within an expression, so you're not using that within the declaration of a method, but you're using that within some block of code. And here, whenever you have that as a statement, you are safeguarding not the entire method, as we were doing before, but just one region of code, which is enclosed by curly brackets. So you might use an object, which might be any kind of object that you are defining, and then you're synchronizing on top of that. So why on earth that might be useful? That might be useful if you want to provide guarantees that of splitting the region of code into different concurrent regions for which you know that, for example, you're not required to have a global lock, but you could also have multiple locks. For example, if you have multiple variables, for which then you could create different objects that are acting as a lock, and then you're doing the synchronization over this. So all the terminology that we were saying in here applies in as much as the synchronization now will use not the entire this as a lock, but that will use basically the object itself as a lock. So you're just restricting to one object, providing the mutual exclusion. Then that is actually the thing that I already stated before, but I'm just reinforcing the concept. Methods of a given class can also be declared as synchronized. In this situation, the object that might invoke such method is the whole lock, but that is not a statement. So the synchronized statement is just this coding here on top. So this is what the synchronized statement is about. And these are just other applications of synchronized. And then if the method is a static one, then the lock is actually my class. So that is actually the thing that I was saying before. And then as an exercise, you could also double check what happens if we replace read and write locks over one single variable with synchronized. And given that you have the code, you could also try to experiment that on your own and see what might be look like. So this is actually the thing that I was stating before. So in here, you could also use the synchronized method to also avoid, one process to lock itself in. So usually in the past you have locks and then they define reentrant locks. So by just revising what I stated before, if you're using like the traditional lock, you might have a process locking itself in. If you're using reentrant locks, you're avoiding that. But using synchronized also allows you to, also allows you to avoid a process self-locking in the case where you have a recursive call. So in here, so that's why I was saying the Java knows whose thread is actually holding the lock at the current time. And so if it knows that basically the same thread is trying to run the recursive call, it's not locking that thread in, so that recursive call is not to create deadlocks at all. Because then the lock is only going to be released after the last, so after all the recursive calls are terminated, basically. So whenever I terminate all the recursive calls, then I'm releasing the lock, so another process could invoke increment. But besides that, do you have questions? So that's it for today. So that's why I'm asking whether you have questions. Because then you have like Diker and Peterson algorithms, but we're going to discuss those today. On Monday, after semaphores. So then you have two choices. Either we terminate early, so you have a longer break, or we start discussing monitors. Any preference? Either starting look at monitors or having a longer break before we continue and we start doing monitors only this afternoon? Yeah?
I've got a question about the reentrant block.
Sure.
When you showed it to us, you just declared it as a lock.
Yeah.
Where would you actually instantiate the reentrant
Good question. So I was saying that beforehand, but the idea is that I showed that also in a slide. So that could be like in the constructor, or whenever you're declaring the field, you're doing equals like reentrant lock. So that might be one way to go. So that's why I was saying, you also have, where is it? I think that should be like the AB3. Object monitor, yes, this one. So the best practice, which is actually covered in monitors, is going to so if you're stripping from the conditions that will be covered either now or this afternoon, you have a lock there on top, which is actually a field of a class. And then in the constructor, you are initializing the lock. So, or you have private lock monitor equals new reentrant lock, which is also like invoking the implicit constructor. Because the way Java works is that prior to the invocation of any specific constructor, it will initialize the fields that are at random within the code. So those will be always initialized prior to the invocation of the constructor. So that's why you might also have seen before, like the open and closed braces within a class, that is going to be run anyhow before the constructor, and then within the constructor you're doing this kind of initialization, which is going to be the same. Anyhow, so that's why if you're declaring the monitor in here, in this method, then each thread which is invoking this method and providing the rationale why that is the case, okay? So each thread that is going to invoke this method is going, as a consequence, to create a new monitor if you are providing like the new instantiation of the lock in here, and therefore, as a consequence, you're not going to achieve mutual exclusion because each thread is going to create a new object which is local to the stack, and therefore the lock is not shared across the objects. Therefore, as a consequence, you're not achieving mutual exclusion, but that gives me actually an opportunity for better explaining that. So why on earth then synchronize is actually a viable alternative? Synchronize is a viable alternative if you do not want to overthink, basically, who is detaining the lock and whether that is shared or not. So basically, if you're using the synchronized method and you're doing like that, it's like having one single field, which is this, acting as an object, and therefore you're going to achieve the same stuff of using reentrant locks. Then another question might arise, which is the following: what is the main difference between them using synchronized traditional Java locks and reentrant locks or actual class locks? Then I think that maybe it's actually going to be better that I answer questions now, given that we have 15 minutes, we don't have time to start anything sensible. Otherwise, we will have more open questions than solutions. Then the thing is, now we just achieved the way to lock everything out, but we haven't thought about waiting conditions for which my execution of the raise condition, of the critical section of code, like the critical section code, might be halted, stopped, and then resumed later on. You have something called waiting conditions. And if you're using traditional Java objects, that are also going to be referred as Java monitors, then you don't have specialized waiting queues for differentiating different waiting conditions. So whenever you want to wait back a process for actually resuming its computation, but that resume is actually dependent on a condition all the threads are waken up, and then they need to test whether they were waking up for the right condition or not. So you achieve also busy waiting. And that becomes actually quite detrimental. And even in the earlier days, they were providing separate waiting queues, so even in the 70s. Basically, with the Java implementation, they went back to that, to the early 70s, and they were saying, okay, you need to wait everyone up, and then you need to wait for the condition. If there's actually nothing is not going to happen. So, actually, the practice went back to Stone Age, and then they resumed, oh, but they have this interesting concept of waiting queues, and then they reintroduced those back. So it's going to be fine if you're going to use this kind of solutions, but you're coding like in the early 90s, where you didn't have reentrant locks properly. And if you have very simplistic code with very limited concurrency issues, it's going to be fine. As soon as you have, like, for example, to implement a strict-to-phase locking, or you have a more complicated program with multiple conditions, then you have to wait a lot of threads, and then you need to remember all the conditions for which the thread shall not be stopped. Shall not be continue execution, because if continue doesn't hold, and then it's going to be a mess. So earlier solutions allows, a higher steeping curve, but then a cleaner code to read. And you don't need to think about all the possible combinations of conditions that are going to happen. You're just waking something up, you're waking the process from the waiting queue, and then you know for sure that that is its due running time. Then for you all, might be seen like trivial. Well, if I'm coding correctly, then then it's actually the same. If I'm using the old method or the new method, and just need to wait for the conditions. And anyhow, even though you have reentrant locks and you have waiting queues, you might actually create errors anyhow. But the thing is, you're adding a layer of abstraction on top, which gives you more control. And given that you have more control, then there are less ways you need to look for bugs in terms of concurrency, and then you're limiting the error to a specific area, rather than looking across all the possible combinations that might happen in the code. So does that answer the question? Okay. Any other question? So just to restate the obvious, that's why in the exam you have written that that is the direct application of strict-to-phase locking, because in here you want to safeguard the execution in this way. So you're assuming that whenever you're declaring or doing operation over a variable, then the dependency, the mutual dependencies of the updates will start from that point onwards. So, you could also achieve, like ChatGPT might provide you as a solution, to, like the braces and belts solution is actually, I have 5 variables, I'm locking everyone out in a lock way, and providing that on top. And then I'm ensuring, if I'm using like an exclusive lock, to lock everyone out, I'm doing my computation, and then I'm proceeding. But that is not guaranteeing efficiency in a realistic solution, because it's going to delay the computation. So, if you have, for example, access to a variable which is accessed in reading, then you shall not use an exclusive lock, but you shall use like a reading lock. So you know, if you are hard-coding the solution and you know basically what the program is doing, you could be more fine-grained. And then in some situations, you know precisely what the computer is going to compute, and you could determine which lock could you provide. So, this kind of exercise is explicitly meant follow the protocol and to achieve some kind of efficiency. Then I know that if you have also deeper understanding, not also on the occurrence of the variables, but also the understanding of the code, you could also be more efficient in terms of the ways I'm releasing all the locks. So potentially instead of releasing all the locks at the end, you could also release the locks at the middle of the computation, because basically I'm ensuring something to terminate. But that's actually why this kind of exercise is on strict two-phase locking, not on any kind of locking. Then in the coursework, you have one way, which is actually the way suggested in the slides, in the marking scheme, to use the monitor being provided for checking these conditions. But there is actually a purpose for everything. So that's why it's strictly required to use strict two-phase locking, not any kind of locking. So you cannot expect an algorithm to automatically understand another algorithm due to the halting problem. Besides that, any other question? Then if not, I'll say class dismissed, then we're going to see each other in 2 hours again. But the thing is that it's not required to be implemented in the way which is described in. But you have plus, which is already using one monitor, and is also doing something else. So the part of the coursework that is actually required is to also wait for events to be handled. So it's going to be basically an extension of that. So you're not required to achieve like, you're not required to achieve a fine-grained solution like across the variables. So strictly speaking, the strict two-phase protocol is doing that all the variables, how do you say, is safeguarding the variables one at a time once they occur. One of the implementation provided for the coursework, you just have a get and a set on which the arbitration of the undistributed source is needed. So somehow a simplified version of the protocol extended to the entire variables. This is actually a more fine-grained from the solution we're going to use the coursework. So the thing that I meant with that, you are not required from scratch. Yes, that is what I meant precisely.
Just like already in the...
Yes.
And is it like going to be
exercise number 4. So if you go to Canvas, you have exercise number 4, and then you have strict two-phase locking. And that is going to weight the majority of the questions. As far as it's going to be like 20 marks all over, if I'm not mistaken. And in there you have the first one, which is just you have a schedule, you need to understand when you have an issue, and then you say, okay, I have this issue, then I need to in place like the exclusive lock or the shared lock in the correct way, and show how by applying the locks you're changing the schedule mode. So that is actually what the exercise looks like. So the thing that you're going to receive is just the scheduler with the issue, then you're changing the schedule, and so you're showing that by applying the locks, you're also forcing the execution order of the computation. And then, in addition to that, you also have, which is the issue, why, fixing the schedule as I said, and then you have the other part, which is how that might look like in Java. Something like that. let me clarify also of the fields that you have. You have like a bijection, so to one-to-one correspondence between question or thread topic name and timestamp. Why? Because you might also have multiple questions being answered, being asked at different times. So you want to ensure somehow, and just will start collecting things, okay, while I continue talking. So you might have like multiple questions asked, so you want to disambiguate which was asked when. So that's why you have a hash map or anything of the like on top, which is association between string and date and an ID. Then you have like an atomic integer, basically providing a progressive ID. And then you have an association between an ID and a thread topic, which is another hash map. Then the other question might be why that is not like an array or a list, and it's an array list or a list, and is actually a hash map. Well, the reason is that you have another method which is actually called delete a topic. You have a moderator which is going to delete something. Then, in order to avoid massive restructuring costs, which are requiring basically the renumbering of all the topics, I'm just saying you just have a hash map, and with that hash map you are just keeping the topic IDs that are still there. So we have 0, 1, 2, 3, 4, and then you're removing, for example, 3, but you have 0, 1, 2, 4. So that's why you have a hash map, so you don't have to restructure everything.
Does that make a unique ID?
Unique progressive ID, yes. And then that's why you have like an atomic integer for that.
Yeah.
So was it a question? Yes.
Yeah, just a quick one. So
Cool.
obviously, I can't believe I waited. Like if I waited 5 minutes, and maybe in that next bit I would have seen the synchronization. But like,
Okay.
but if in terms of the monitor, so I was just while I was watching you go through and kind of the critical conditions, so I know we go through it later in the afternoon.
Yeah.
I was just kind of trying it because it's kind of like with a try and catch almost formation, and the monitor's being used to lock. Do its thing,
Yeah.
and then unlock it once it's done.
Yeah.
So it's like instead of having a synchronization locking the whole thing down,
Yeah.
you're doing it essentially in the methods where you
Yeah.
lock, unlock, and then between the lock and the unlock is where the method takes place.
Yeah.
You just so the structure is use your monitor to lock down what that method is doing whilst it's doing it, and then once it's done, unlock, and then it signals that it's done basically.
But so we could also move the discussion also outside. That's fine. You don't not so that is actually one part, but that is actually merely syntactic things. But the reason why we're going to see monitors is also for the structure of the waiting queues themselves.